My screen is visible. Okay. Yeah, fine. Let's start with today's agenda. Okay, so yeah, hello and welcome everyone to the ninth lecture of our CUTA program. Okay, so typically in the previous lecture, we saw about memory coalescing, right? So we saw like when the warp thread accesses the words from the same block of 32 words, their memory accesses are clubbed into one single memory access, and that single memory access memory request is given to the provided to the memory controller. And yeah, and then we also saw how this memory coalescing is implemented at the hardware level, and typically how this SIMD execution of the warp threads is exploited to implement the memory coalescing. Okay, and then we also saw multiple examples for the memory coalescing. So like we saw the example when the memory accesses are fully coalesced. Then we also saw the example when the memory accesses are partially coalesced, and third case we saw that when the memory accesses are completely uncoalesced. For that also we saw the example. And yeah, then we also saw then we saw that arrays of structures and structures of array thing. Uh, so we saw how to declare those data structures in the previous lecture, and we also saw um, how to access those data structures in the kernel, GPU kernel. And yeah, and then we also saw that SOA data structure is better for the GPU than the AOS data structure because the memory coalescing property is exploited in better manner in the SOA data. SOA data structure than AOS data structure. And yeah, probably there we ended for the last lecture. So yeah, that was the kind of outline for the previous lecture. So for today's lecture, I'm planning to cover this shared memory part. So we'll be covering multiple aspects related to the shared memory for the today's lecture. So we'll first of all see for the today's lecture, we'll first of all see how to use the shared memory. That is what we are going to see mostly for today's lecture, and we'll also see multiple examples related to it so that we can understand how to use the shared memory. Then we'll see some things, some synchronization construct across the threads of the block. We'll see what is that synchronization construct, and we'll see multiple examples about how to use that synchronization construct. Yeah, for that we'll look multiple examples, and towards the end we'll also study about how to specify the size of the shared memory of the L1 cache where that we want to use. Yeah, so that is what we'll study in today's lecture. So that's a quite overline for the today's lecture and outline for the today's lecture. And with this, let's get started for the today's lecture. So yeah, so this was the last slide probably that we saw in the previous lecture. And just for the recap, this is the way we declare AOS data structure, and this is the way we declare SOA data structure. So yeah, so one thing is that this AOS data structure is better suited on the CPU because as you can see, this the way we declare this AOS data structure is this, and when such kind of declaration is there, and when we have CPU thread which accesses an attribute of a node, let's say that attribute is A, CPU thread is accessing the attribute A, then it is likely that it will also access the other attributes of the same node. So it is likely that it will access this attribute B and C. And the way this data structure AOS is stored in memory is that A, B, and C are contiguous in the memory. So since they are contiguous, the caching effect will come into play. More precisely, this locality aspect will come into play, and due to that, we will be able to see uh, performance improvement on the GPU, on the CPU. Sorry, on the CPU, um, and hence this AOS is better on the CPU. I mean, better to use on the CPU. In contrast, we have this SOA data structures of arrays. So here on the GPU, what happens is okay. So this SO is better on the GPU because on the GPU, what happens is when a thread accesses an attribute of a node, that is, let's say, thread is accessing an attribute A of this of a node, then its neighboring thread will access the same attribute of the next node. So the neighboring thread will also, it's likely that neighboring thread will also access this same attribute A. So in that, if that is the case, then it is better to put the same attribute of all the threads together. So if you see here, we have placed the attribute A of all n threads together in this array. So by doing this, we'll definitely get the benefit of memory coalescing. And since the coalescing will be better by storing in such a manner, such SO data structure fits well on the GPU and will give better performance as compared to AOS. And in AOS, we saw in previous lecture, right, that on GPU it leads to strided access, and that degrades the coalescing, memory coalescing. Okay, so that's a sort of a brief recap till the for the previous lecture and about the AOS and SOA. So let us start with today's agenda, which is the shared memory. Okay, so before I start, is there any question quickly in the chat? Okay, not yet now visible. I hope that the screen is visible for everyone. If it is not, then please let me know prior. Okay, I think it's visible for all. Okay, yeah, I think there is no issue with the sharing, is what I'm supposing. And there are no questions also. So yeah, let's move on. Yeah, so let's move on. I just got confused with it. Yeah, but let's move on. So let us start with our today's agenda, which is shared memory. So as I told in the earlier lecture of the memory, that there is something called as L1 cache, and that L1 cache is splitted into two parts. First is the L1 cache itself, which is managed by the hardware, and the second part is this scratchpad memory or the shared memory, which I keep on telling that it is programmable, and I kept on telling in the few of the lectures, right, in the memory lectures, that the scratchpad memory or the shared memory is the portion of the L1 cache which is programmable and is under the hand of the programmer. So programmer can specify that okay, this part of this I want to declare a variable which should be stored in the scratchpad memory or the shared memory. So we'll see how to do that here only. And yeah, so this one thing here that you should observe is that this is kind of a very powerful feature that is provided by CUDA, because if you know, on CPU there is nothing like this. I mean, there is no control. I mean, there is no programmer cannot control what data goes into L1, L2, L3 or L4 cache on the CPU. Programmer has no control over it. It is completely under the control of hardware what data is placed in those caches on the CPU. And also programmer has no idea about how that data is arranged, inside those L1, L2, L3 or L4 cache. But here in CUDA or on the GPU, if you see, yeah, please go ahead. Was there any question? I think there was some noise from or some question from someone. If there is question, then please go ahead. Okay, anyways, if there are no questions, okay, so as I told that this is kind of a powerful feature provided us by CUDA, because like on CPU nothing, I mean these caches are completely managed by the hardware, and programmer has no control upon what data to place on that cache as well as the way it is arranged. But on GPU we have this portion of L1 cache, which is scratchpad memory or shared memory, which can be I mean programmed by us or the programmers. So that's kind of a important feature that we should exploit and which is given by the CUDA. The next important point is that this scratchpad memory or the shared memory is per thread block. So I mean, so each thread block will have its own scratchpad or shared memory. And one point that you should remember here is, like, even though multiple thread blocks are assigned to the same streaming multiprocessor, even then each thread block will have its own shared memory or scratchpad memory, and all the threads which are within the thread block will So the thing is like the variable which is I mean declared in that shared memory will be common across all the threads which are there in the which are there in that thread block. So yeah, so the important point to note is that it's per thread block, and yeah, and the threads within that thread block will see the same will see the same copy of it. Yeah, so that's the second point. And the third point is that it is typically useful for two cases. I mean, mostly it is typically used for two cases. First case is that there is a small amount of data, small chunk of data, which is getting repeatedly accessed by the threads. So let us say that you have a very small array, which is getting used repeatedly by, I mean, which is getting accessed repeatedly by the threads within the thread block. Then in that case, it is very useful to keep that small array or small that array into the shared memory, so that the latency of accessing that array is very less, because this it is the part of L1 cache, so access latency is very low. So yeah, so that is one typical use of it. Second is coordination. So if you remember, I told that L2 cache can be used to implement fast atomics. In similar way, let's say if you want to implement some synchronization construct among the threads of the thread block within the threads of the thread block, then it is more useful. I mean, it will be more convenient, or it will be more uh, proper to use the scratchpad or shared memory instead of L2 cache, because we want to implement the synchronization construct among the threads of the thread block and not across all the threads of the across the thread block. So since this scratchpad or shared memory is for the thread block, I mean for the threads of the thread block, what we can do is we can keep a variable which can be tested and set atomically in the shared or scratchpad memory, and in that way we can implement some functionality of a barrier or something like that to coordinate the threads within the thread block. And this is one of the another use case in which we can use the this scratchpad or shared memory for implementing the for implementing some synchronization or coordination construct among the threads of the thread block. So yeah, so these are typically two uses for it. And now let us see how to declare a variable or an array inside the shared memory. So okay, so please remember that it is a per thread block. So yeah, so I'll come to it. What that means with this example. So first of all, whenever we want to declare a variable or an array inside the shared memory, we need to precede it with the this keyword underscore underscore shared underscore underscore. So rest all things are same, if you see. So let us say then okay, yeah, so rest things are same, but let us say that we want to declare the float array of size n. So this is the typical declaration in C, float a of n. But when we precede it with this shared keyword, then what will happen is this entire array A, which is of size n, will be allocated memory on the, will be allocated space on the scratchpad or shared memory. And the important point to remember here is that it is common across all the threads of the thread blocks. So let's say the thread block has 1024 threads, which is the maximum possible number of threads inside the thread block. So those 1024 threads will be sharing this array A. And yeah, so that's one case, declaring the array. Second case is that we want to declare some variable A, variable S on the shared memory. Then the syntax is similar. We need to precede it by the shared, this underscore underscore shared underscore underscore keyword. And then this type of declare, this syntax is same as the C, right? The data type and then the identifier. So again, this variable S is now declared on the shared memory or scratchpad memory, and it is common across all the threads of the thread block. So let's say again, if we have 1024 threads in the thread block, then all these 1024 threads will have this common, I mean, they will share this variable S, so that this variable S will be common across all these 1024 threads. So compare this with this normal declaration. So please note that this all things are happening inside the kernel. So let us say if you don't specify the shared keyword here, then what will happen? Let's say only this part is there inside the kernel, unsigned as. Then this variable will be a thread local variable inside the kernel. And so when it's a thread local variable, so thread 0 will have some value of s, thread 1 will have some value of s, and thread 1 cannot access the value of thread 0, and thread 0 cannot access value of s of thread 1. So that is what is thread local when we declare just as unsigned as. But when we declare underscore underscore shared underscore underscore unsigned as, then this variable is common across all the threads of the thread block. So if thread 0 and thread 1 are within the same thread block, then they will be able to see the value of s as well as to modify the value of s, because it's a shared variable, and both of those threads are falling in the same thread block. So that is typically one point to note here. Yeah, so moving on, then let's say we have this kind of assignment a of id equals to id. So one important point to note about this sort of assignment is that now this id here, this id which I'm using here and here, it can't be the global thread id the way we compute, right? The way we used to do, like int id equals to thread id x dot x plus block dim dot x into block dim dot x into block id x dot x, because that equation that we generally used was giving us the global globally unique thread id. But here this if you note, this array a is shared among only the threads of the same thread block. So we'll need to compute the id which is unique to the threads of the sorry which is unique to the threads of the thread block. So what can be this id? uh, can anyone quickly tell what can be this id? We want the id unique to the threads of the thread block, then how can we compute this id? Just quickly, I'll move back to the chat to see if people. Can you quickly explain fast atomic second? Okay, so let us say we want to implement a functionality where, let's say, multiple threads are adding the value into particular variable. Then in that case, since multiple threads are adding the value into the same variable, there is the possibility of data race. uh, so since there is the possibility of data race, we want to synchronize. We don't want multiple threads to add the value at the same time. So for that, we'll need something called as atomics. We'll learn about it in the synchronization lectures. But to implement that functionality, we need to have a variable which can be tested and set atomically. And for doing that, we need to declare some space. We need to declare space for that variable, either in the L2 cache or the global memory. Since we want to implement it across all the threads of the grid, we need to declare that variable in L2 cache or global memory. And yeah, so it's so as I told in the one of the lectures of memory, it is better to keep it in L2 cache because the accesses will be quick to that variable, because L2 cache is closer in the hierarchy, in the memory hierarchy, to the GPU core. But here our requirement was different, right? We want to synchronize among the threads of the same thread block. In that case, instead of using even L2 cache, we can use L1 cache. So that was what I was trying to explain. Do we declared a shared array variable inside kernel or main function or separately? Okay, so shared variable and all those things are declared inside the kernel. So yeah, so just to clarify that point, this entire thing is inside a kernel. Please note that this shared and all those things are completely inside the kernel. There is nothing like shared inside the main or CPU functions. So this is typically for GPUs. GPUs meaning inside the kernel. Okay, block ID. Okay, you are telling that this ID should be block ID. No, I don't think that it should be a block ID. So okay, so the question is this array shared, I mean it's declared as shared, right? So it's I mean it's common across the thread of the same thread block. So in that case, what should be this ID? I guess someone answered. Yeah, Harish said thread ID x dot. Yeah, this is correct, because since we want a unique ID for the threads within the same thread block, it is I mean we should use thread ID x dot x, right? Because thread ID x dot x gives the unique ID of thread inside the thread block, provided that we are just having one dimensional thread block. If it's a 2D thread block, then we'll also need to use thread ID x dot x and thread ID x dot y. But yeah, in in the case where we have just one dimension thread block, thread ID x dot x should suffice for our purpose. So this ID should be thread ID x dot x, and this will initialize this array A. And please remember that this all things are done inside the kernel. And yeah, and then there is this statement: if id equals to 0, then we set s equals to 1. So what this does is, for the first thread of all the thread blocks, please note that for all the thread blocks, the first thread of that thread block will initialize this variable s to 1, and this s is common across all the threads of the thread block. So all the copies of s which are per thread block will be initialized to 1. So yeah, probably I'll stop here for a moment. If there are any questions, then I'll quickly take them. If there are any questions. Okay, I guess there are no questions. If there are any questions, then please either unmute yourself and ask, or you can even type on the chat. Okay, if there are no questions, then let us move further. So let us start with this classwork. So let us say that we are given an matrix M of size 1024 cross 1024, and each row is assigned to a thread block. So okay, so since there are 102, it's a 1024 cross 1024 matrix. There are 1024 rows, and each row has 1024 elements. So for each row, we are assigning a thread block, and assuming that thread block has 1024 threads, we can assign one thread for each element in the matrix, which is Mij. And if that's and yeah, if one thread for each and every element of the matrix. And what we want to do is we want to change Mij, which is that particular element of the matrix, to Mij plus Mij plus 1, wherever possible. Meaning for last column it won't be possible, right? Because for last column there is no j plus 1. So for rest all column except the last column, we want to do this. We want to change Mij to Mij plus Mij plus 1. Okay, so for doing this, we want to exploit the shared memory. So I request each and every one of you to try this out and post your answers in the chat, or either unmute yourself and ask. So I hope that question is clear. Each row is assigned to a thread block, and since there are 1024 threads in a thread block, what we want to do is we want to assign one thread for each element. And what that each thread does is it does Mij plus Mij plus 1 and stores into that location Mij. And for doing that, we want to exploit the shared memory.
I have a question, sir.
Yeah, please go ahead.
So Mij plus Mij plus 1, let's say one of the indices I comma j is updated with this. Then, however, that value is also going to be used by the adjacent thread to update Mij plus the next Mij plus 1, right? So, i- like, because the whole thing is happening in parallel, what's the value sort of we are expecting? Or should we store the results in a new matrix? Or?
No, we want to store the values within the same matrix. So we won't be using any another matrix. But yes, you are correct that there will be this issue that as all the operations are happening in parallel, there can be some inconsistencies in values. But yeah, for that we'll need some sort of synchronization construct or something like that. But first of all, let us think about how can we do this. I mean, can you give some rough steps to implement this thing, and how can we exploit shared memory here? You are correct that we'll need some thing to synchronize, because we are accessing this to location, and adjacent thread will be also accessing this too. So there might be some inconsistent value that we might be reading. But yeah, that is one issue. But first of all, think how can we implement this and how can we exploit shared memory. Okay, I'll probably go back to that slide, so that I'll wait here for a few seconds and for you people to try, and then we'll continue. Okay, I'm hoping that you people are trying. Okay, so I'll wait here for a few more seconds, and probably then we'll continue. Switch. Okay, you can create separate shared vector for the rows to the computation and construct a matrix out of. Okay, I think this is quite doable. I mean, we can do this. But okay, I am assuming that you people have tried, and let's move to the slides then. So okay, so we want to implement this functionality. So how can we do this? Like, what can be step-by-step way of implementing this? So let us see this. So step one would be to first of all we need to copy the data, copy the row from DRAM to shared memory, right? Or first of all we need to declare the shared memory. So how can we declare? Uh, okay, so there are multiple. Okay, okay. So we'll before this step, what we'll do is we'll declare the shared memory. Uh, Shared int ARR of size 1024. Uh, yeah. So this will come before this step one. So after that, we'll copy the data from DRAM to shared memory. That is the step one. Then step 2 is we'll do computation, right? Computation using that formula m of ij equals to that whole thing, right? M of ij plus m of ij plus 1. That is step 2. And what is step 3 is okay, so one point here is that I can't use m of ij right now because we need to use shared memory. So once we have copied the data from shared memory, what we'll do is we'll use ARR of ij equals to ARR of ij plus ARR of ij plus 1, right? We'll do that. That is step 2. And step 3 is we'll copy the ARR values to m per row, per each row we'll do that. So these are typically the 3 steps that we need to do. Copy the data from DRAM or the global memory to the shared memory. First of all, declare the shared memory of size 1024. Then for each row, copy the that row from DRAM to the shared memory. Once that is done, we'll compute whatever is there in the shared memory. Once we have copied, we can use that shared memory and then compute using our equation here. But now we don't need to use m because now we have the values available in the shared memory, right? So we can use that data in shared memory and can perform computation like this. And once that is done, we need to copy the values back from shared memory to the global memory into that matrix m. Okay, so I hope that this is clear. If there are doubts still in these 3 steps, then please let me know. So meanwhile, I'll take some, view some responses by you people. For I equals to 1, I less than 104, I plus plus. Okay, so this is fine, Nancy, but this is the CPU code, right? What you are suggesting is the CPU code. You want to do it on GPU. So for doing it on the GPU, we need to write a kernel, and inside kernel we need to do all these steps, right? So that is what I'm suggesting. So these are 3 steps we'll be doing inside the kernel, because shared memory we need to declare inside the kernel. Then copying from global memory to shared memory we want to do it on kernel, and then computation on kernel, and then again copying back from shared to global memory or that array m again on the kernel we need to do. And mallocing and all those things will be done from the CPU, right? That is allocating the memory for this array m and initializing it and all those things. We need to do it on CPU and then copy to the GPU. So before declaring the shared variable, will we allocate memory in GPU using CUDA malloc? Okay, so that I need to clarify one thing here. For declaring the shared memory, you don't need any CUDA malloc or all those things, because so for shared memory you don't need CUDA malloc and all those things. Only for declaring the memory, allocating the memory in the global memory, that is DRAM of the GPU, you need CUDA malloc and all those things, and that need to be done from the CPU side. But for declaring the shared memory, you can do it from the kernel. So as I told, if you remember these things, all these things are done on the GPU. It's inside the kernel. It is done on the GPU. So when you declare this thing, shared float A of n size n, it's on GPU. This is inside kernel. And it will allocate this array A per thread block. Array A is per thread block now. So I hope that's clear. Any further questions?
Yeah, so the step 2 should be single array manipulation, right? Not to the ARR of I equal to ARR of I plus ARR of
Why singular?
I.
Sorry.
My understanding was the shared memory we will per block is essentially for a row, so you have declared it as ARR of 1024, which makes sense. That's the first step.
Oh, okay. Yeah, I got it. So it should be, yeah, that is correct. It shouldn't be ij. That's a syntactic error that I've made here. So we need to access it in the way. Okay, so we just for the clarification, we need to access it like this. We need to access it like this. So that is one thing, that is correct. But any questions up till this point? If there are any questions, then please ask. Otherwise, I have few questions for you people. If there are no questions from your end, then I'll ask you people a question. Okay, I'm assuming that there are no questions, and you people have understood this thing, and this steps you people have understood. Assuming that you have understood all these things, now there are two issues with respect to this. Okay, so first of all, we are exploiting the shared memory here. If you are seeing, we are exploiting the shared memory, but okay, that is fine. So our this final thing is achieved, exploit the shared memory. But still, there are two issues with respect to this procedure, or this three steps which we are doing to achieve our functionality. I want each and every one of you to tell me what are those two issues with that. So first issue, I think Varun or someone specified that uh, this thing is problematic because we are accessing this. I mean, we are doing this operation in parallel, and uh, threads. I mean, threads will be concurrently accessing this ARR of I and ARR of ARR of ij and ARR of ij plus one. So there will be issue that two threads might be accessing it. I mean, might be reading the same value together, and that value might be wrong. So that is one issue. So let me explain that thing with example. So let us say that we have this some random values. Let's say 5 and 7, 8. So let us say that we have some array like this. Now, uh, what computation we are doing? We are picking two values. I mean, we are let's say for the index one, which is having value 35. What we are doing is we are taking that 35 and 2, and then adding those two and placing it at this location, which is this, and so this will become 37 now. But at the same time, what the neighboring thread is doing, it is picking this value 2 and 5 and placing 5 plus 2 at this location. So it might happen that neighboring thread have placed here 7, and after that this thread here, which is computing, I mean, which is operating on this element 35, does 35 plus 7. So in that case, the value will be 42, which is wrong because the actual value should be 37. So that is first issue that was specified by someone. But still there is one more issue here in this entire the procedure, which is composed of three steps. I request each and every one of you to see and tell me what can be the another issue here. So uh, yeah, please try out like what can be what might go wrong here in other than this thing, other than that this this part. Is there possibility that we may go beyond our defined size of 1025? Yeah, I mean, assume that we have taken care of the boundary checks and all those things. Assuming that, what can be the issue? I mean, yeah, it is possible that we may go beyond 1024, but assuming that we have written it perfectly, I mean, we have done the boundary checks and all those things. Uh, if that is the case, then we won't be encountering this issue. But there is still, I mean, still some more serious issue here, just than this boundary checks and all those things. In these three steps, I mean, if you observe it carefully, you will be able to see that there is some critical issue here which might cause correctness issues. So please think about it and tell me what can be the issue. Meanwhile, I'll wait here for a few seconds to for you people to try out. uh, is some response. The order of execution of threads will differ the final matrix. No, I don't think so, because we'll be calculating the we'll be calculating the ID, right? So based on ID, we'll be doing all the computations. And even let's say, as long as a thread is picking the value of that element and its neighboring element and adding and placing it in that element, I don't think that that will cause any issue, Rishikesh. I hope that is clear. But yeah, I don't think that order of execution of threads will differ the final matrix. Or if I'm misunderstanding something here, then please correct me. Between two thread blocks also we can have neighboring values, and we can between two thread blocks also we can have neighboring values, and we can't access shared memory of one block from. Okay, so okay, there is one confusion here. I think Varun, you are slightly confused here. So see, what we are doing is we are declaring this shared array, or this for this array of size 1024 for one particular row, right? So what we'll do is we'll perform only operation for that particular row, and there is no need for so okay, so let me go back to this. So what this equation, the way we are computing this is that we are bringing the entire row out of all this. Let us focus on one row. Let's say we are uh, focusing on the zeroth row, and that zeroth row is assigned to a particular thread block, right? Now, since threads, there are 1024 threads inside that thread block, and since each of them are performing their uh, computation independently, and let's say the last thread is not doing anything because there is no j plus 1 for the last element of the row, right? So let's say 1023 threads are doing their work properly. In that case, they don't need to access anything from the shared memory of the next block or the previous block, because everything that they need is inside is already brought from this matrix inside their declared their declared shared variable, and they can use that for computation, and there is there is no need for accessing the shared memory of previous or next block. So I don't think any issue is there is any issue from that side. Yeah, so if there is any still there is any confusion, then please let me know. But yeah, there is no need of accessing the shared memory of uh, any other thread blocks. Sir, so we still have the inner for loop in the kernel, right? Inner for loop in the kernel. No, I don't think that we'll probably need any for loop, because see, what we are doing is wait, yeah, there will be one loop, because yeah, there will be one loop because we'll doing this operation repeatedly, right, for each and every row. So yeah, there will be one loop, but will that be the inner loop or not? Yes, I'm not sure, but yeah, there will be still one loop, because we'll need to do this operation repeatedly for each and every row. So there will be one loop, yeah. Okay, I guess we are okay from doubts point of view, but yeah, so um, we were unable to point any issue here, but that's okay. So there is still one issue, as I told, there is still one issue in this three steps that I mentioned. So the issue here is that let us understand what is the issue. When you are copying the data from DRAM to shared memory, first of all, you are declaring the shared memory and then copying the data from DRAM to shared memory. And then in the step 2 you are doing computation. So can it happen that some threads have not finished the copying, and other threads reached here at the step 2 and they started they started with the computation? Or can it happen that some threads are still doing the computation, and other threads reached here and they started copying the data from the shared memory to the DRAM? Can this thing happen? is the question. I want to ask this question to you people. Can this thing happen? So like, can this thing happen that we are few threads are still copying the data from DRAM to shared memory, while other threads came here at the step 2 and started executing this thing. Can this thing happen? Quickly, I'm asking this question. So is it possible that this type of execution flow might occur? Is it possible? Divergence, I didn't got your point. Okay, I think that okay, so let me continue with this. So I asked this question, right? Can it happen that this some threads are copying the data from shared memory, DRAM to shared memory, while some another threads are doing this operation? So I must clarify here that this thing can happen, and this thing will happen typically for the threads which are in the different warp. So if you see, few of the warp threads might be copying the data from DRAM to shared memory. Meanwhile, let's say some another warps have already finished that step and they moved on and they might be doing computation. So if that is the case, then you can see that this copying is not yet done, but still that computation has started. So this is problem because we want this computation to finish, this copying to finish and then the computation to begin for all the threads of the of this thread block. So all these 1024 threads of the thread block should first copy the data from DRAM to the shared memory and then only move towards the computation. And then once the computation is finished, then they should for all the threads of the thread block, once the computation is finished, then only they should move towards the copying the values back from the shared memory to the DRAM inside the matrix M. So in order to do this, if you see carefully, we need the synchronization point at two places. One is here between step 1 and step 2, and another is here between step 2 and step 3. That is the two, those are the two places where we need the synchronization point, synchronization construct, and we'll learn what will be that synchronization construct probably in today's lecture only. And the second thing is, as mentioned by someone, as multiple threads are performing this operation concurrently, ARR of ij is equals ARR of ij plus ARR of ij plus 1, and they are placing their values in ARR of ij. We'll also need to have synchronization construct here because multiple threads are reading the values and writing the values. And as we saw here, like with this array example, right, that there might be some inconsistent values which might uh, which might occur due to this type of execution. So those two things we need to take care of. So some synchronization construct we should have at between step 1, step 2, step 2, step 3, and while during this computation. So yeah, so that was the point. So these are the issues with this typical execution flow, and we'll see what is that synchronization construct with the upcoming slides. But any questions till now? Okay, I guess there are no questions. Then let's move on. Okay, I'm assuming that you people have understood what I was trying to explain with the shared memory and the classwork here that we discussed. So let us see. Let us see this program. So here we are first of all defining the block size to 1024. So each block will have 1024 threads. And then coming to main, we have this kernel launch in which we are launching the kernel with one thread block with 1024 threads inside each thread block. So there are, in short, total 1 into 1024, which is 1024 threads. So kernel is launched with 1024 threads, and yeah, and then we have this CDS, CUDA device synchronize. So CPU will wait here for all the threads of this kernel to finish. So here we have launched kernel with 1024 threads, and then I'm declaring this variable s to be shared across all the threads of the thread block. In fact, here we have just one thread block, right? And there are 1024 threads inside that thread block. So this variable s is shared across all the threads of the thread block, and then we are doing some initialization and addition on that variable. So if thread id is 0, then we are adding, so we are initializing s to 0. Otherwise, when id is 1 or 100, we are adding 1 or 2. And then finally we are printing that variable s. And I want you people to think about what can be the output of this program. So I request each and every one of you to try out what can be the output of this program. Can there be multiple outputs, or can there be just one single output? And if there is single output, then what is it? And if there are multiple outputs, then what can be that multiple outputs? So what are the typical values that we can get by, by the execution of this piece of code? So I'll stop here for a few seconds. Request each and every one of you to try that what will be the output of this program. And yeah, please try and post your answers in the chat, or unmute yourself and please unmute yourself and tell the answers and whatever your thoughts are about it. Please try. Let me go back to the chat. Yeah, I'm assuming that you people are trying. I'll quickly switch back to the. So please try out what will be the what are the possible output for this code snippet, and try out and post your answers in the chat. Rishikesh is saying multiple possible outputs, 3 and garbage value. Okay. Varun is saying 3. Okay. Any other possible outputs apart from this 3 and garbage value? Or anyone wants to support this garbage value answer? Let me go back to the slide. So I'll wait for a few seconds more here to let other people try, and please try and post your answers in the chat. So after a few seconds, we'll move further. still let me go back. Rishikesh is saying garbage won't appear 0. Okay. Okay, 3 I can understand that 3 will be uh, one of the value that can be printed. But how can 0 appear is I'm thinking. Any supporting statement that you want to make, Rishikesh, for this 0? Then Varun is saying 1 or 3 or garbage. Okay, I think this answer is really very close, but still we are missing something. This is really close. Okay, I am thinking that you people have tried. Probably I should move back to the slides, otherwise. Yeah. So let us understand this code. What are the possible outputs that this piece of code can give? So first of all, you should understand that we are just launching kernel with one block, and so this shared variable, there will be only one copy of this shared variable across all these 1024 threads, which are there within just single thread block with which we are launching the kernel. So this variable as is shared across all 1024 threads. Now, okay, now let us say that yeah, we have this common variable across all the threads. Now, what will be the typical execution flow? So thread 1 initialize the variable as to 0. Thread 0, thread with ID 0 initialized as to 0. Then thread with ID 1 made s plus equals to 1. So it incremented the value of s. So value of s is now 1. Then thread 100 incremented the value to 2. So its value is now 3. And then thread 0 printed the value of s, which is 3. So 3 is one of the possible output out of this code snippet. But what can be the other possible outputs? So let us understand this code in more better way. So first thing that you should observe when you are solving this type of questions is that uh, first thing that you should always keep in mind that warp threads execute in SIMD fashion. That thing always you should keep in mind. And we have just one thread block, and which has 1024 threads. So there are 32 warps here, and so the first warp is from 0 to 31, and second warp is from 32 to 63, and so on. So 32 warps, and each warps execute in SIMD fashion. So when I say that warps execute in SIMD fashion, first thing that you should observe here is that uh, this statement thread id x dot x equals to 0, then make s equals to 0, then this statement, this thread id x equals to 1, then make s plus equals to 1, and this statement print when thread id is 0, we print the s. This three statement will always be executed in lockstep fashion, this and this. So there is one thing for sure here. This will be executed, then this will be executed, and then this will be last printf will be executed. So this order is fixed. There is no change in this order. But but the thread which are not in that warp, which is the warp number first warp, which is having threads from ID 0 to 31. The threads which are not in that warp uh, can be executing in arbitrary fashion. So the thread which is not there in that first warp is this thread with ID 100, right? So even though these three statements, this statement, and this last statement execute in lockstep fashion, which is one after another, this statement, which is being executed by thread with ID 100, which is not there in that warp, uh, it can be interleaved in any fashion. So following are the interleavings that are possible. So see, uh, this thing s equals to 0, then uh, s equals to 0, then s plus equals to 2, then s equals to 0, then s plus equals to 1, then printf s. This is one of the order that can happen. Second is s equals to 0 can happen, then s plus equals to 2 can happen, then s plus equals to 1 can happen, then printf can happen, or this thing can also happen as equals to 0, then s plus equals to 1, then s plus equals to 2, then printf. Or one more possibility is this: s equals to 0, s plus equals to 1, then printf s, and then s plus equals to 2. So these are the 4 possibilities that can happen, assuming that these are the 4 possibilities that can happen. But there are also few more possibilities, but these are the these are the 4 possibilities among the total number of possibilities that can happen. So if you see properly, for all these 4 cases, answer would be either 1 or 3. So if you see in the first case, answer that printf will give is 3. In this case, it will be again 3. In this case, it will be again 3, but in this case, no, sorry, for first case it will be 1. For first case it will be 1. For rest 2 it will be 3, and for last case again it will be 1. So printf here will give 1, then here 3, 3 and 1. So for this 4 case, if you analyze properly, answer could be either 1 or 3. But my question is, can there be more possibilities? Can we get something else from the printf? So I think Varun has suggested something, and Rishikesh is also suggesting something. Garbage value won't be printed, 0. I don't understand how 0, but Varun is saying either 1, 3, garbage value, or 2. Okay. Yeah, I think this answer is correct. This 1, 3, garbage, and 0. Okay, so yeah, so we have understood why 1 and 3 can come, but Varun, do you want to explain why garbage value or 2 can happen? You can unmute yourself or you can type in the
Yeah,
chat.
I wanted to quickly look at the code if that's okay.
Yeah.
The garbage value is when the 100 belongs to the fourth warp, right? So then that executes first. And
Then,
in that case, the value is not initialized at all.
okay. Then,
And the value
and
of 2 was,
how can be the garbage? Let's say this happen as plus equals to 2 by the 100 thread.
yeah, and uh,
How can then be there be a garbage?
that is a thought of it in a different, probably not the right way.
Yeah.
I probably didn't think about it the right way. Okay.
Yeah, but anyways, whatever you thought you can put. Even if it's incorrect, don't worry about it. Just it's important to highlight what you think. So that is what I want to emphasize. Just don't worry about the correctness or anything. Just whatever you think, you can.
Oh, oh yes.
Just
As far as I remember, I did think of the last statement as warp uh, ID as 0 rather than thread ID. So that's what I made a mistake.
okay. So if that's the case, then you might think that garbage won't be printed. Is that correct?
Yeah.
Okay. Let us see what be the case. Rishikesh is telling something. Sir, when ID is 0, won't it also print the value 0 like it would enter to if statement in the same thread? Okay, yeah, I think we are missing out something here, Rishikesh. Like uh, threads execute in lockstep, walk threads execute in lockstep fashion, if you remember from our previous discussion. So here, when the thread all the 32 thread of the walk will come, they'll set s equals to 0. While that, so this will be executed only by the thread having ID 0. So only one of the thread will execute this. Rest all will be masked out. After that, they'll be moving to this statement. Then they'll be making s plus equals to 1. So s will be 1, and then they'll move here. So I don't think that 0 will be printed in either of the case. 1 can be printed, 3 can be printed, even something else can be printed, which we'll see. But I don't think that 0 can be printed. If you have any thoughts about it, then please you can type here, or even unmuting yourself and ask, saying is okay. Okay, got it. Okay, so first thing is that we understood why can we get 1 and 3, but there are still two more possible outputs here. First is 1 and second is 3. Third possible output is 2. So even 2 can be printed here, and the fourth possible output is garbage value. So 1, 2, 3 and garbage value. These four possible outputs are here. We saw how 1 and 3 can occur, but we need to still see how 2 and garbage value can be printed here. So let us try to understand this, but let me just quickly check. Okay, there are no doubts. So how can there be, how can the output be 2? Let us understand that. Let us say that, okay, let us understand this. Let us say that thread 0 was here, and okay, first of all let us understand this, that this thread 0, 1 and thread 100, these are in the different warps. So thread 0 and 1 is in one warp and thread 100 is in another warp. So it might happen that whenever this thread 0 was initializing this s value to 0, okay, at that time, let's say this thread 0 has initialized the thread value to 0. This statement was successful. So threads now this shared variable s is now its value is now 0. And then let's say that thread 1 from that same warp started executing this statement s plus equals to 1. Meanwhile, the thread of the warp, thread of this warp where this 100, this thread with ID 100 is present, it also started executing this statement s plus equals to 2. So in that case, what can happen? This 2 statement s plus equals to 1 and s plus equals to 2 are now executing simultaneously. So there is a data race here. So either this will be successful operation or this will be successful operation. Assuming that the second operation is successful, so okay, first of all understand that s value is initialized to 0, and now these two are executing in parallel. So assuming that only one is successful and assuming that the second one is successful, the value of s that will be that will be that will be present in this variable s after execution of this two statement will be 2. So I hope that you are getting, s was initialized to 0, then these two were happening concurrently, and since they were happening in the same, at the same time, either of two will be successful. Either of two, either of either of this two will be writing finally to the variable s. So s can either take value 1 or 2, because this addition of 1 or 2 is happening here. And assuming that this is getting successful, this statement is getting successful by this what where the thread with ID 100 was there. So the final value that will be there in this variable s will be 2, and then let's say thread 0 prints the value, and in that case we'll get the output as 2. I hope that's clear. If there is any confusion here, then please let me know. We'll resolve it.
Similarly, why can't 0 cannot be printed? Because at some times,
yeah, sorry, yeah, please go ahead. How can 0 be printed?
When thread ID.x is 0 simultaneously,
okay,
all the threads will be running parallelly, no, sir?
Only warp, threads among different warps will be running in parallel, as I mentioned. So threads from 0 to 31 are executing in SIMD fashion. So it won't happen that thread with ID 1 is executing this, thread with ID 0 is executing this. If you remember our SIMD execution, then all the threads within the same work, which are in this case, it's the thread from ID 0 to 31, they are executing in SIMD fashion. So first this statement will be done, and then only they'll move to this statement. And if that's the case, output 0 is not possible, because this statement should be done, and only after we can move to this statement. If this would have been done before and then this would have been executed, or if let's say these two would have been done and after that this s equals to 0 would have been executed, then output 0 is possible. But here it is not possible because of the SIMD execution of the work threads. I hope you are getting it.
Okay. Okay, sir.
Yeah. Yeah, we'll come to this. When I executed the program, I got output 3. Yes, output 3 is the output that we'll be seeing in most of the cases. But what we are trying to analyze right now is what are all the possible outputs. If you see output as 3, then it doesn't mean that is the only possible output. There can be multiple possible outputs. And we have seen so far that why can we get output 1, why can we get the output 3, and why can we get the output 2. But still there one thing is left. How can we get the garbage value as the output? Would anyone like to explain or give some convincing explanation for why can we get the garbage value as the output?
S
Think again.
equal to 0 and S plus equal to 2, both of those execute uh, parallel
Yeah.
simultaneously.
In that case, how can we get the garbage? Can you explain it
Because
more?
S won't be initialized for the 100 thread ID, and so it will add garbage plus 2, but and that will win the race, and then it
Okay.
will go
Okay.
ahead and add 1 and
I think that's correct. So let us understand how can we get the garbage here. So as I said that threads which are not in the same work can execute in any fashion. So in that case, this if condition or this statement s equals to 0, which will be executed by the thread with ID 0, and this statement which will be executed by thread with ID 100 can execute in parallel, right? These two statements. And if that is the case, then it can happen that the value of s, which is initially garbage value, is read by the thread 100, is added with the value 2, and is written back before this s equals to 0 is written, sorry, after this s equals to 0 is written by this thread with id 0. So the value that this thread 100 will write is garbage plus 2 in the s, and then thread 1 what it will do is it will again read that garbage plus 2 value, will add 1 to it, and will write garbage plus 3 in that variable s, and then finally this thread with id 0 will print this value, which is garbage plus 3. So okay, so far we have seen these three possibilities. One is 1, 2, so 3, garbage plus 3, right? Now I have still one more question for you people. I think my spelling for garbage is wrong, but yeah, please assume that this is garbage. Can we get garbage plus 2 as output? My question is, we have seen these three, right? 1, 2, 3, and garbage plus 3 as four possible outputs that can occur out of this program. Can we get garbage plus 2 as the output? I'll quickly move to the slide so that you can think about it. Can we get garbage plus 2 as the output? Okay, Varun is saying no. Okay, why no, Varun? Do you want to give some comments for that? Why you are assuming that?
The only comment I have is essentially the 0 and 1 threads belong to the same work. So
Okay.
um,
How then? How? Yeah. Please go ahead.
after the 0, the statement corresponding to s equal to 0 is executed, along with which s plus equal to 2 is executed in parallel. The
No, no, no. Okay, please understand here that they are not executing in parallel. Since they are verb threads, they are
no,
executing in SMT fashion. So this will be done, then only this will be done.
I was talking of 0 and 100. 0 and
Okay, okay.
100.
For that, it is correct. Yeah. Then go ahead. How can you say that it's no?
Uh, the execution of s equal to 0 and s plus equal to 1 has to happen, and the race condition will be at, at most at one of them, either at s equal to 0 or at s
Yeah.
plus equal to
Race
1.
condition will be either at this place or this place. It can't be at
And
both.
then
That is
one
correct.
other statement has to execute, is what.
Uh, It is not the case that other statement has to execute, but yeah, let us see what will happen. I think there is something that you are missing here, but yeah, let us understand it. Let others, let's see what others are suggesting. Okay, Rishikesh is saying yes. If you are saying yes, how? I mean, when if you are saying no, then how? And yes, then why? I mean, you should add some um, conclusive argument to your. Yeah, please go ahead.
Sir, am I audible?
Yeah, you are audible.
Sir, so like I'm not sure, but like if the race condition is between the third and the fourth statements, like we initialized it as 0, added 1,
Hmm.
and print between printf and s plus equals 2 if there is race condition.
Yes, I think that is correct. So let us understand why garbage. Yeah, so answer is yes, garbage plus 2 can also be printed, but let us understand why it can be printed. So let us assume that these two statements happened in parallel, s equals to 0 and s plus equals to 2. So initially the value readed here will be garbage. Here also it will read garbage because yeah, both will read garbage value. Now let us say that this 100 thread read garbage value. It added to that 2 to that garbage value. So the result was garbage plus 2. Okay. But before storing that garbage plus 2 into s, what happened is that okay, so that storage is pending. So before happening that storage by storage here, what happened is that here thread 0 assigned value 0 to it, 0 to the s. Uh, uh, it did s equals to s plus 1, and okay, so here the value of s was 1, but after that this thing happens, storage of garbage plus 2 to the s. So the final value of s will be garbage plus 2, because here 0 was stored, then 1 was added, then 1 was stored, and then finally this garbage plus 2 which was computed here by the thread 100 was stored in the s. So the final write that happened to the variable s, if the order of execution which I told would have happened, then the final value of s that would be there would be garbage plus 2, because the final write what was done by this thread, uh, which was having that garbage plus 2 as the computed value inside it. So yeah, garbage plus 2 will be there, and then finally thread 0 will print garbage plus 2. So yeah, 5 possible outputs: 1, 2, 3, garbage plus 2, garbage plus 3. I hope this is clear. If there are any questions at this point, then please ask, because I think there might be some confusion among you people. But yeah, please feel free to ask the questions here. If there are no questions, then we'll move further.
I didn't catch again. So how
Okay.
when you have garbage, the thread ID 0 and the first warp has already increased it and changed the shared to 1, right? How can it still be garbage when the thread ID
Let,
100
let
is?
us understand. Let us understand this. So yeah. So initially, if you assume, I mean, Yeah, I'll explain garbage plus 3, but let us first understand garbage plus 2. So initially S was garbage, right? Okay. Now this garbage value is read by read into the local registers of this both the threads, right? So this thread 0 and thread 100 will have garbage value read into that local register. So let us understand this. So whenever I say S equals to S plus 2, something like this is happening on any thread, what is happening is this will happen. This single statement will be broken into 3 statements at the assembly level. So this register equals to S will happen. S will be read into the register. Register equals to register plus 2 will happen. Then S equals to the register will happen. So this single statement is broken into these 3 statements. Now let us say that this thing here, this statement here by thread 100, it read the garbage value as per this or this here. So this register now has garbage value. Okay, is it okay till now, Varun?
Yeah.
Now let us say it has read garbage value. It did garbage plus 2 here. Now this register has garbage value. So garbage plus 2 is there and it's stored inside the register. Okay. And okay, so this register is storing garbage plus 2. Now what will happen is, let's say this this writing is still pending. This garbage plus 2 is writing in S is still pending. Meanwhile, what happened is this S read the garbage value, made it to 0. Then this thread 1 also incremented it to 1. So S was written 1, but the value of S is finished will be garbage plus 2, because the register is storing garbage plus 2. And here the last thing that will be done is garbage plus 2 will be stored back in the S here.
Right. Understood.
So finally this garbage plus 2 will be there, because this one is the one which is doing the last operation. And after that, if thread with ID 0 prints, then it will print garbage plus 2. I hope that is clear. Okay, garbage plus 3, I'll quickly repeat why can it happen. So again, as I explained here, that this statement S equals to S plus 2 can be splitted into these 3 statements, right? So what might happen is, let's say this value of S which was read here will be garbage. Here it will be garbage, here it will be garbage. But let's say this thread with ID 0 initialize the value of S to 0, but before that the value of S which was read as garbage here which was read as garbage here will add 2 to the garbage and will store garbage plus 2. So since these two things are executing concurrently and the S equals to 0 is written before this, so final value that will happen, that will be there, will be garbage plus 2 after execution of this. And let us say that after that thing, this thing is executed, S plus equals to 1. So S is having garbage plus 2, doing plus 1 to it will give garbage plus 3. And the final value that is printed will be garbage plus 3. So total 5 5 outputs are possible: 1, 2, 3, garbage plus 2 and garbage plus 3. I hope that's clear. Okay, I hope that that is clear. If there are any questions further, then you can ask here. I'll hold here for probably a few seconds and then we'll move on. Okay, I'm assuming that it's clear. So my next question is simple. Let us just quickly look into what we can do with this. So my next question is very simple. Let us say, so there are 5 outputs possible here, right? But let us say that we want to restrict the output to just one value, which is 3. Then how can we do this? Is my question. This program gives multiple output, right? This program gives multiple output because of this parallel execution between warp, first warp and the warp which is having thread with ID 100. But in order to restrict it to just give one output, what can we do here? Think about it. Please post your answers in the chat. Okay, yeah, so one of the suggestion is make 100 as some less than 32. Okay, something less than 32 is okay. But let us say that we want to keep it as 100. Still we want to get the output as 2. Then how can we do that? Sir, do we have any control in getting any one of 5 different outputs? No, we don't have any control. It's completely dependent upon the way the execution will proceed. So if you execute this program multiple number of times, then you might see that there are multiple possible outputs. So let us actually see what will happen. So, okay, let us say I am executing this program once, then it is possible that I get output 3. Let us say that I execute this program once, but with 2 thread blocks now. Please note that I have made thread blocks here as 2. Then in that case also I get the same output 3. But let us say that I ran this program for multiple number of times. Let us say I just ran it with 2 thread blocks, each of 1024 threads, but with within the loop of 0 to 10. In that case I'll get 20 possible output because 10 iterations, each with 2 thread blocks, so 20 possible outputs. So if you see here, you might see somewhere here 1. And this indicates that even though 3 is the most likely output, but the other 4 outputs that we discussed, which are 1, 2, garbage plus 2 and garbage plus 3 are also possible if we execute this program multiple number of times, as you can observe here. So I hope this is clear. Okay, I think we have overshot the time. So okay, I'll wait here for a few seconds to take up the questions, or a few minutes, probably 2-3 minutes I'll be here for taking up the questions. If you people have any questions up till this point, then please ask it by unmuting yourself or post them on the chat. Any questions up till this point from any of the slides till here? Okay, I got your point, Varun, that we can make 100 as something less than 32, or yeah, something less than 32. But let us say that our computation is such that we can't make that that value as less than 32. Let's say first 32 threads are already busy doing something. Then in that case, we need to pick some thread having ID more than 32. In that case, how can we solve this problem? Probably we'll look this in the next lecture. So probably next lecture we'll see what is the synchronization construct that I was telling at the start of that lecture, that we need to synchronize the threads of the same thread block. So that will come into the picture here for making the output deterministic. Here the output is not deterministic. It can be any of that 5 value. But to make the output deterministic, we'll need that synchronization construct that I was talking, which will synchronize the threads of the same thread block. We'll see that in the next lecture. But meanwhile, any questions? I'll be there here for a couple of minutes. Sir, out of the 5 different, is there something as correct output or incorrect output? I mean, is as equals to 3 considered correct and rest as anomaly? See, when it comes to parallel execution, there is nothing like correct or incorrect. There are 5 possible outputs, I will say. But let us say that as a programmer, when I wrote this code, my expectation was that I want to get the final output as s equals to 3. Then in that case, I'll say that these 4 outputs that I'm getting, which are apart from s equals to 3, are not as per my expectation. But let us say I was writing this code in such a way that I wanted to see how can this data arrays affect the final result. Then I'll be not astonished by looking at this 5 different outputs. So yeah, it depends upon the programmer's perspective, I'll say. I hope that answers your question, Harish. Okay. Okay. Meanwhile, any questions? If there are any other questions, please feel free to ask. Like priority encoding, can you elaborate, Ramasam? Like what, like priority encoding?
Say which one you are writing first, that happens, and probability most of the time it will give the same thing.
Yeah. Yeah. I mean, there is probability that one particular order of execution will happen multiple times, but that's the not only one that, I mean, that can happen in this case. That's what I'll say. There is one possible order which can happen most likely, but has high probability of occurring. But there are other also, I mean, there are other also possible orders that can occur. And yeah, I mean, you can compare it somewhat like priority encoding, the way you were suggesting. Okay, any further questions?